Okay, let's assemble the other channel. And that's really what this video is going to be. A little solder and talk. And I have the camera at a little bit of an angle so I can get in here to work, because it's just kind of, it was in my face the other way around. And now, if we would have built this amplifier the way it came when it was purchased, it would be built on this circuit board, which would be a little bit easier, I think, because you would just match up the component names that are on the screening here on the board, place them in there and solder them up. Now we're doing point-to-point wiring. I'm doing it for several reasons. Number one, I just like the look of a point-to-point wired amplifier. Also, it makes it easier for this series for me to just do a little part at a time and then power it up and test it. If we'd used the circuit board, we may have had to, take the board out and put it back in, and it's kind of a pain with the wires on it and everything. So this is a lot easier. And but really, there are advantages and disadvantages to both. And if you lay things out the right way on a point-to-point wired amplifier like this, you can get it to be pretty quiet. And there's a lot of, I saw this on YouTube, or read this on the internet, and all of a sudden I'm just going to repeat it, and I'm going to chastise everybody who doesn't do it exactly the way I read it on the internet. Well, the truth of the matter is, some of the things you hear have a kernel of truth to them, but not everything you hear is 100% truth, especially when it comes to different types of grounding and things like that. Again, all of these things have conditions to them. For instance, about how to run your filament leads. I've found, just in my experience, and again, I'm not just, I could be right or wrong, but in my experience, twisting the filament leads like this is very effective at reducing any kind of radiated hum to the rest of the circuit. Keeping the filament leads away from certain parts of the circuit, kind of like we've done here. Like this is, if you notice the way this thing's laid out, I have the power, all the power related things clear over here on this end of the amplifier. The transformer, power switch, the mains input, the rectifiers, and all of the things that take place before that first pi filter are all happening way over here. So you could just draw a line right here on this amplifier, and everything on this side is power and can have mains hum on it. And everything on this side has what we would call filtered. I won't call it regulated, because this is an unregulated linear power supply, but it at least has the filtered DC over here. The only AC that you have is low voltage, which is this 6.3 volt filament winding, and by twisting the wires together, it helps to cancel out any noise that there might be from that, because they're equal and opposite magnetic fields that each line is creating because of the direction of current flow. So when they're twisted together, they just kind of cancel each other out. It does a really good job of it. Anytime you're going to cross them with a wire, try to cross at 90-degree angles like this. It helps. There's a very small amount. When wires are parallel to one another, they can radiate or capacitively couple to one another much more easily than if they're crossing each other at 90-degree angles or perpendicularly. So again, little things like that. These wires here are all high voltage wires, either going to the output transformer or to the power supplies themselves. They have mainly DC on them, although the output transformer can have some AC due to the signal that's there. But again, it's very low frequency, and with this type of wire, not going to be an issue. This green wire is going to be for our global negative feedback line, and it terminates up here on this side and here for this channel. So there is a method to the madness. The capacitors, the filter capacitors, I'm keeping them all on this side as well. The way this amplifier is designed, at least the way it came, one power supply is controlling both channels. So if you look here, some amplifiers out there will have two sets of all of these. So you'll have your main feed right here where your rectified first filtered power is, and then this will branch off and you'll have two of these dropping resistors, one for left and one for right channel and so forth. But if you notice, see where it says to right channel? So this one resistor creates the power source for right and left channels together. Now, because of that, here's those dropping resistors that were in that line and their associated filter capacitors. And again, I keep them to the right here. And then all I did was I jumpered over to this terminal strip for symmetry. And these are the voltages that are going to branch off and go to this channel here. Some of this stuff's not used yet because we haven't connected it. And even some of this is not completely wired up yet because we haven't wired anything into the preamp or phase inverter section. So we'll get to that in another episode. But for right now, that's the method to the madness. Now this one, the way it's laid out seems to be working really well. And yes, here is a film capacitor. It's a pretty good quality one. And some people really get hung up on outside foil and all that. And in my opinion, in my experience, these smaller sized capacitors just don't seem to have a problem with that. And if they do, you're really putting them near something that's really radiating a lot of electromagnetic interference for this to pick something up if it were put in backwards. So I'm more concerned with the layout of the amp than by worrying about the direction of the outside foil, and I know I'm going to piss a lot of people off with that. Look, if you want to check this and flip them around however you want, feel free. I mean, it doesn't hurt anything for sure. I'm not going to tell you not to do it. I'm not going to tell you you have to do it. I'm just going to tell you how I do it and let you make your own choices. This is your project. If you're going to build one of these, it's your project. You build it your way, the way you like it. I mean, that's how I see it. So anyway, enough about all that. Let's put this side together and try to make it look like this side. Now, I think a lot of you are used to seeing my Hakko soldering iron, and it's actually part of a soldering station that I have. And yeah, these, you're going to have to make a financial investment if you want these. The handle and the tips all are sold separately, and you can buy many different types of tips. And then the actual modules that drive, the power modules that drive them, you can get this one's connected to the FX951, which is the first one I ever had from Hakko or Hakko, however you want to say it. And then I also have a larger multi-channel station to drive the bigger iron and the desoldering tool and all that. But you don't need that. So what we're going to use is something that's I call old reliable. And this is something that I have had for many years, and I actually have several of these, and I love them. And these are the Weller model, let's see here, model 8200. And you can still buy these. The cases are either made of a type of hard plastic or Bakelite, depending on when it was made. The earlier models had this metal strain relief on them. The later models, they did away with this. They're just excellent soldering irons. The later, they have newer updated models now that are not called the 8200. They're in a more modern kind of red and black plastic case. The case is actually less chip resistant than these old ones, but the switch on them is horrible. If you buy the new Weller soldering gun, the switch doesn't click like this one. If you listen, hear how it clicks, and you positively can hear it click between the 100 and 140 watt. See, the new one does not have a click in the switch. As you're transitioning between the 100 and 140 watt power settings on the switch, you can actually kind of click it in between where it disconnects. You can kind of hear the switch arc internally when it reconnects, and it kind of makes a popping noise. They're not going to last like these do. These things last a really long time. These are one of the best kept secrets on the internet. You can go on eBay and buy a used one of these for under $20. Now, you may have to pay a little bit of shipping, but all of these I bought for less than $20 each. And I love them because there's nothing to go wrong with them. They just work, and you never really have to worry about them. You pick them up, plug them in, they work. The tips, you can just use a piece of copper wire, just a piece of mains, number 12 gauge wire. You can actually bend it around into the shape and it'll work. You can buy these long life tips. They make ones that are copper, and they also make ones that are plated, and they last a really, really long time. They heat up really quick. They have a nice little headlight on them. Makes it easy to see. I love them. So we're going to use this and see how to solder with one of these. Okay, I try to work with the larger components that are going to be underneath on the chassis first, and then I work my way up to the things that are on the pins and the terminal strips second. So like you notice, I have most of my wires run and all of that sort of thing. And now I'm going to put this cathode bias resistor. Now, a couple of different ways to mount these. These are really small. Even though this is a 10 watt wire wound resistor, it is relatively small. So it's kind of hard to find a small enough nut and bolt to fit on there, because the head of the nut will hit the end of the body of the resistor. These holes are really, really tiny. So what I do, again, this is up to you if you want to do this, I will either use a number 440 SAE screw, or in this case I'm just using some M3, and you can see how small the M3 screws are. And I use these little things that are self-drilling taps. You can buy these online, relatively inexpensive. You can buy cheap ones. If this is only aluminum, you don't need to buy really high carbon steel ones. These ones are good. They're high-speed steel. But you notice it's an M3. And it has a drill bit on the front, and then it has a tap connected to it. I don't know if you can see that. So it'll drill the pilot hole through, and then once it pops through the pilot hole, it'll tap it. And you just put this right in your drill. And all I do is I put this in my little mini vise to hold it tightly by this ear. And then I just drill this through and tap it. So this is tapped for a type M3 screw that you can just thread right in there then. And then that allows you to screw it down from the outside of the chassis. And then all I did here, if you notice, was I drilled a couple of holes to match up with it. And although I did the calculations and the actual wattage on this is not going to be real high. So for instance, if let's say we have a maximum of, let's just say 20 volts voltage drop across here. It might go a little above that during peaks and so forth, but let's just say there's a 20 volt drop across there. And we know that somewhere, it's going to be somewhere around, let's just say 75 milliamps. So 20 volts times 0.075. So it's dissipating about 1.5 watts. And it could be a little higher than that. So let's just say 2 watts. And this is a 10 watt resistor. So it will get warm because it's a smaller physical size, but it's not going to get blistering hot. So what we're going to do is we're going to put a little bit of heat sink compound on it, and we're going to couple it to this chassis. And between the chassis, the oversize of the resistor, and the fact that it's only dissipating 2 watts or less, this should run relatively cool. It's not going to get hot. It's not going to damage or melt anything around it. And it's going to last a really long time. So that's what we're going to do. So I will get this right here. And I'll just put just a little bit of this on there. And this is going to be a mess. And I'm going to be off camera. And I'm sorry, but that's kind of the way it's going to have to be till I get this started. Kind of hard to hold these things. But I mean, this is kind of how you build something like this. And again, I kind of prefer myself the point-to-point wiring. I like the looks of it when it comes to vacuum tubes. I just like the way it looks. Down the road, it's easier to work on. You might think a circuit board's easier to work on because you can desolder the component from the board, but really what ends up happening is when you build that board, if you notice, that board has a whole bunch of little standoffs. In other words, the tube sockets, here's one in here, they solder right onto the board like this. And then you have these little standoffs that screw into here, and they protrude up. And then you would put the board down and screw through the other side of the chassis into this board. So you have a whole bunch of these screws, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 screws holding this thing in. And you would have to take all those out to get under the board to properly desolder it, unless you wanted to heat the leads up from the top and pull through, which you could do, but you don't always get the best soldering job putting it back in. And you have all these wires going onto the board. It makes it very difficult. This way, it's actually pretty easy to get to these wires and to just, desolder the terminal, pull the wires off, put the new component in, you're good to go. So you can see we have this all wired up, and we're going to get a little piece of green wire and a snip, and we have to go from here to our ground, which is going to be over here. And while I'm doing this, another thing you get a lot of comments on is the grounding. A star ground versus a bus ground versus a chassis ground. There are certain circuits that you will be building, that you'll see out there, that the grounding is absolutely imperative that you do it a specific way. And usually that has to do with components or circuits that involve RF or involve very high impedances and very low signal levels, where that sort of thing can really, you can get an induced hum very easily into the circuit. This is considered a power amplifier. In other words, it doesn't have a real high gain preamp like you would in a guitar amplifier or a phono stage or something. So the only part of the amp where there's a lot of gain taking place is right here in the front in these two input tubes, which are pentode tubes. And anything, in there, you could possibly get some hum. But from the grounding, as long as your connections are very tight, this is a stainless steel chassis. It's not going to corrode or rust in any way. And as long as these connect, and yes, stainless steel doesn't have as good of a conductivity as copper, but it has very good conductivity. It'll be fine. And as long as these connectors stay tight, none of these come loose, you will have a good grounding system from the chassis. If you're worried about it, you can connect your ground terminals together. A lot of people say that you could induce a ground loop from that. Again, things that you read about, but in practice, there has to be the right conditions for something like that to induce a ground loop. So I'm not saying it's impossible, because I have witnessed it, I have seen it, but I'm saying that in some instances it's probably, from my experience anyway, not a big issue. And this amp, there's been many of these small amplifiers built with a chassis grounding system like this, and they have absolutely no hum. They work fine. Again, when you have problems with hum, it is more often than not the component placement or the quality of the soldering and wiring that you do that causes the hum, more so than some a capacitor is not facing the right way with the outside foil, or you use chassis ground instead of bus ground. So again, it's just my observation working with this stuff. Okay, so let's take this up and we'll run it along here, or we could also run it around this way and come in. And I kind of like that. That looks pretty good. I can bundle that in with all of those. And again, these things are all connected to ground, so you're not, this tiny piece of wire isn't really going to make a point for hum to be induced. You can't have a big enough voltage drop across this little area for there to be hum. Again, take everything you read, even anything I say, with a grain of salt. You really need to experience some things to really know for sure how they work. There are lots of good classes out there, lots of good books and things like that that will help you learn things, and they can have some very accurate information from people's experience. But I say this as you're watching this on the internet, but a lot of things you see on the internet you can't always 100% believe, and that's why I tell people not to always believe everything I say, because do your research. I'm not a professional. I try to admit that to you guys up front, that I'm not an expert on the audio thing. This is a total hobby to me, and I'm learning, and you're learning along with me when I do this. But by no means would I ever call myself an expert at audio electronics. There's people who do this sort of stuff for a living and have done for many, many years, and they're very good at it. Those are the kind of people you want to talk to. There again, I don't know that I would want them working on a $500,000 CAT scanner or something, because they know electronics, but that's a different discipline. And the same way, I would never claim to be as good as them on this type of stuff. So take everything with a grain of salt, and do some experiments for yourself to find out what things, how much reality there is to what you hear. Don't just believe everything you hear. I have people get really belligerent on the comments sometimes about something, and it's funny because their belligerence is based on something that you can tell they're just repeating what they've heard on another video or read somewhere on the internet, but have never experienced or tried for themselves to understand how it works. And never ceases to amaze me that people will put that much credibility into something without actually knowing the facts about it. So I warn you that. All right, now what we're going to do is we're going to make the connection to the pin 3s. So here's one pin 3 is here, the other pin 3 is here. We're going to jump one connection from here to here, and then we're going to go from here to the resistor, and then we're going to take the resistor, we're going to bypass this resistor with the bypass capacitor. And remember, we talked about this in the last video. This is the cathode bypass capacitor, and its purpose is to alter. Under DC conditions, this capacitor does nothing. It just sits there across the resistor. But once it charges up, it has no influence over current flow or anything. No current will flow through this during DC conditions. So when the amp is sitting idle, everything is being handled by this resistor. As soon as you start putting changes in current through this amplifier, or changes in voltage, however you want to word it, as soon as you have that change in current, this capacitor, again, will act like an RC time constant, and it will influence that signal. And really, the rise time of that signal, or shall we say the frequency of what signal we're putting through there, will determine how much influence this capacitor is going to have. It's a balancing act, like we always say. And what it does is it can influence the frequency response of the output section of the amplifier. So we can either make it more bass heavy, more treble heavy, or even flatten it out based on what value of capacitor and what type of negative feedback we're going to use from the transformer. So all these things work together, and you can experiment with it. Sometimes you don't want a really totally linear frequency response because it may affect the overall sound at the end of the day, especially when all the circuitry is working together. You may not want that. You may want it to be a very linear response curve. The other thing is, at certain frequencies, with certain capacitances, it could actually make the amplifier have more distortion in some instances, although that distortion to your ear may sound good. And I'm saying all this from the standpoint of an audio amplifier, like a hi-fi amplifier. When we talk about guitar amplifiers, it's a completely different subject than audio, than audio amplifiers, or amplifiers that are used for hi-fi. And the reason I say that is hi-fi amplifiers usually want low distortion and flat frequency response, whereas a guitar amplifier, you want those things to change dynamically as you change the way you play your instrument into it. So there will be purposely built things, what you would call flaws in here, you would purposely put into a guitar amp to make that particular sound. So interesting stuff. All right, do we want to connect our capacitor this way and take it to ground here? Or we can run it this way and ground it to this like this. Or we can use one of our ground terminals back here, which is what I think I'm going to do. I'm going to put that back there, just because it's going to fit there a lot better. Okay, we're going to put a piece of this Teflon tubing over here. And again, we have our filament lead there. So what I'm going to do is, and again, there's a very low voltage drop between here and ground, less than 20 volts. And the current is relatively high compared to an electromagnetic interference. So I'm not so worried about this, and the wires are twisted, but I'm still going to run it somewhat perpendicular across here. So when I put this in here, I'm going to come in like this. I'm going to angle this a little bit. I'm going to run this up in here like so. And we're going to try to get something that looks a little bit like this. I may have bent that in the wrong place. I might want to adjust that a little bit more. So let me redo this. Like I said, your lead dressing is pretty important, and you don't want to. Now, some people like to, move the label around so you could see the value of the components and all that, and that's a good practice. I mean, I don't do it very often. Bad Tony. But nothing wrong with doing that. Again, it's a matter of preference. You can be as neat or as sloppy as you want. I won't judge you. The only thing that I will comment on is if there's something that's so bad that it really, really affects the performance of what you're building, or more importantly, poses a safety hazard. I mean, I've seen a lot of things with flying leads and so forth, or where high voltages are close to areas where you can physically come in contact with it and touch it. Those sorts of things, I think, I gotta say, you need to be more cautious and do better work. But other than that, it's your project. And at the end of the day, you have to live with it, not me. So let's connect that one. And that's the one I'm going to kind of take around here. And then I'm going to use another little piece to go onto the resistor. I'm roughing everything in right now. And then we'll fine tune it here once we get everything where we want. Just hook that there to hold it out of the way for a moment. And I kind of like all of the leads to kind of come off at the same angle. I've found that if I kind of let these twist around the sides of the terminal instead of kind of lapping up over the top, they end up sticking out, and then it makes it possible for the leads, or easier for the leads to touch one another and short out. So I always try to do it that way. So you just wet the solder joint and then let it flow down into the terminal, and it should look really shiny. I don't know if we can zoom in a little bit to see what it looks like. Turned out okay, huh? I don't know if it's not focusing so well. There, how's that? Okay. As long as you can still see, I'll keep it zoomed in like that. You can kind of follow along with what I'm doing. Now this side here of the capacitor is connected directly to ground, so we really don't have to insulate this if we don't want, and there's no other leads around here that are going to interfere with it. So that's up to you. I like to make nice crisp 90-degree angles. Sometimes these thinner component leads don't allow you to do that as well as some of the thicker leads, but I'll still try that nonetheless. We're going to bend that around. We'll tack that one down. I don't know if you could see over here or not. I might be a little bit off frame. All right. And then we'll cut the excess off of there. Okay. And we'll get that like that. And you can see we're kind of crossing perpendicular over that filament lead. These filament leads are also tied to ground through that center tap of the transformer. So, you know, these filament leads are very close to ground as far as noise and so forth is concerned. So now I'm going to take this underneath here. As I struggle to reach through here. Okay. And we'll straighten that out there in a moment. But at first, we just want to kind of rough this in. And this lead dressing, I mean, a lot of it is just for eye candy, but in some instances, it is also for being able to keep the noise down. In this case, it's not such a big deal. And I'll run this underneath here again. I just messed up my nice 90-degree angle, but like I said, you rough it in and then you finish it up. There. Okay. It's funny. People get into these so much, no matter what I do or how I do it. You should do it this way. You're ruining it. Although I like those comments because when they dispense with all the emotion on the comments, there's a lot of constructive, I won't call it criticism, constructive comments that I get And I've learned things that never really thought of before, and helps me be better at this. Because like I said, I'm not a super professional expert at it. All right. Let's see, is the camera still recording? Yes. All right, and this side we can solder in. This is pretty decent wire that I'm using. It's made by Remington, and it's a copper core with a like a silver tin on it. It's tinned with kind of like a silver alloy. Pretty decent stuff, and it's only like 300 volt rated, or maybe a little more, but it's not super high voltage, but it works really well, and I've had good luck with it so far. You can buy this stuff online. There's a lot of places that sell it. I think you can even buy it at like Mauser's and DigiKey and stuff, but I think they even sell it on places like Amazon and sites like that. Even possibly eBay may sell it. I don't know. But it's good stuff. And again, here is our cathode. Now, with respect to this resistor and so forth, there's some places, again, not in these low gain audio amplifier applications, but some applications like when you're getting into radio and RF and transmitters, things like that, when you have bypassed resistors with caps, it becomes more and more important that the cap and the resistor are bonded together at the leads, like how I have these separated on some other, like RF applications. This might cause a big problem. So again, some of the things you see in one place may have a completely different situation in other applications. So it's not a one-size-fit-all when it comes to wiring things up. So, and I think some comments you get come from people that work with radio circuits or people that work with audio that don't work with radio, or vice versa. You see things like that. And yeah. Okay. So we're going to put that right there. Okay, so there is our cathode circuit. And now the next thing we're going to do is we are going to wire our power to each pin. So the first thing we want to do is we want to get, let's see here, we want the pin 1s, which is here. Let's see here. Let me zoom way back. So we got our pin 1s. We have this going through this 10 ohm resistor that we talked about in the last video, going to the blue wire, or yeah, the blue side of the transformer, and then the yellow side goes through this 10 ohm into this pin 1. So I have these identical layouts. So in this side, the yellow is here, the blue is here. So on this side, the yellow is here and the blue is here. So these guys are going to be the same, and these guys are going to be the same. That's how we're going to do it. So you can see, just like I have these two inner terminals going to the yellow and the blue here, I have these two inner terminals going to yellow and blue here. So we're going to just pick off with our 10 ohm resistor, and hopefully we can get over here to pin 1 with that. It's going to be a stretch, but hopefully we can make it. And then we have our other 10 ohm resistor, which is going to go from this yellow over to this pin 1, and we can reach that real easily. So let's see if we can find our 10 ohm resistor. And with these ones that have 100,000 stripes on them, with They actually have a little more accurate reading for their rating because of the extra stripe. So you have the, let's see, black, brown, and brown, and then gold, meaning a times 0.1 instead of times 1. So that would be black, brown would be 10, and then the second, this is actually not a multiplier on these ones, but the third digit, which would be another 0, so that would be 100. The gold stripe means times 1/10 or times 0.1, so that would mean 10. And then this red stripe tells you the tolerance, which I think is like 5%. But they're different. They're a little bit different color coding than the three band ones. So anyway, we'll measure it, and it's 10 ohms. So these are it. Okay, so first thing we want to do is we want to look and see if we can get to pin 1 from right here, and we can. It'll make it. It's going to be a little bit tight, but it'll make it. So let's get some more Teflon tubing. Remember, that's pretty important stuff on this because you know, these are crossing real close to a lot of terminals and things. And I'm going to cut these so that they'll just let the wire protrude ever so slightly, so we don't need them to stick out real far. Just like that. And then I'm going to move this over to give me a little bit extra space. So I'll heat this up. There we go, just like that. And then we'll take this, and I might need to take just a little bit more off of this. There. And then bend this around like so. Pinch it on there like that. And the thing I like about this Teflon tubing is if you overheat it, it doesn't really melt. It can take really high temperatures before it melts. So you can see there. That's good. Then we'll take this around and we'll make it real neat here after we get this routed. So we'll put this piece on right here. Making sure I'm still in frame, yes. And we'll take that through, just like this. Always make a good mechanical connection too. I mean, you could just push that through there and not hook it around and pinch it, but you want a tight connection. Remember, tube sockets and vacuum tubes run very hot. And what you don't want, if something, you know, if that solder joint comes a little bit loose or something, you don't want the wire coming off of the connection. So this kind of helps keep a nice mechanical connection on there. Now that we have it run, and that's the other thing I like about the old carbon comp resistors. They knew that they were going to be used in vacuum tube applications, so the lead length was longer on them for point-to-point wiring. And on these, you know, on these newer designs, these newer resistors, they have shorter lead lengths. But well, it is what it is. We just kind of work with what we have. If it were much further away than that, our other alternative would be to you know, to kind of spiral coil a piece of real thin lead wire there and extend it. But I don't like to do that unless I absolutely have to. So now this one's going to be a short run. It'll be just fine. So we're just going to have to put a little tiny piece of the lead on each one of these, which will be easy. And before I cut this other side, I'll run the lead first and see how much length I need on the other side. Just like that. We're adapting this chassis that was pre-punched. And it was pre-punched for a circuit board design, and we're adapting it to point-to-point wiring, so some of the things we may have put in a little different location had we had the choice, but we're working with what we have. So this is not the ideal component layout for this, but I think it's going to be just fine. There we go. Go to pin 1, we'll bend that down a little bit. And just like that. Get in here, trim that off, bend this down a little bit. See if we can get a little neater bends on this thing. There, kind of like that, so it's not sticking up at a huge angle. There we go. Okay, so we have that. So our plates are now wired. Now, let's see, I'll zoom you in a little more. You probably didn't see a whole lot because I wasn't zoomed in too well. Okay, now let's take our screen grid, and we're going to have these dropping resistors. And if you remember, they come off of this wire right here, or I mean this one right here. So if you see, we have this 1K resistor, and it goes up to here, and then it goes to the other channel. So we're going to come off of that lead, which is the orange wire, which is this one right here, and we're going to see if we can reach this right over to pin 2, which we're not going to be able to make it from here to here on this one. If you take a look, we don't have the lead length. Now this one we might be able to get over to, I'm sorry, pin 2, yeah. We might be able to get it from here, but this one to here is going to be too far, so we may have to extend that one. I don't like big long leads. They don't look neat. And second of all, having things moving around in there is never a good thing. So we try to keep those things to an absolute minimum. So this one goes from here to pin 2, and we've got plenty of space for that. So let's start out with it. And we'll put it over here. Again, some people, when they build these amps, they look like an absolute work of art. And that's one of the advantages if you're building from scratch. If you take a chassis and you kind of lay it out according to what you're trying to do, you can really make these things look nice. If you're taking something that's already been partially cut and, you know, laid out, you're more limited of your component layout, kind of like we are here, but you can still try to make it neat, which is what we're doing here as best we can. So I'll put this over here. And the purpose of these resistors is to drop that B plus voltage so that there is a voltage difference between the screen grid voltage and the actual anode voltage. And by having a voltage difference between them, that's what's going to allow the amplifier to work in tetrode or pentode mode instead of what we would call triode mode, where you have the screen grid tied to the anode. Triode mode will tend to have lower distortion. It will also tend to be more linear, but it will have markedly less gain and power. So, you know, what would be, you know, a 12 to 14 watt amplifier in pentode mode will only be maybe a 7 or 8 watt amplifier in triode mode. So as we say, again, everything's a trade-off. So here we go. And here's that. Now this, before I solder it down, we're going to kind of bend it to make it a little neater. And then we'll finish this up when we get this one running. We can see we can almost get it there, but it'll be like a banjo string if we do. So we're going to put an extension on this one, and I'll show you how I do that as soon as I find my bus wire. So the first thing we're going to do is find some wire that we can use to extend this with. And that's this stuff right here. And what I do is I will take this and I will coil it like this. As tightly as I can. And once I get a couple of turns on there, I'll take my pliers and I'll pinch those coils together so they're all tight. And then I'll use the pliers to tighten it around there, because you want a really solid mechanical wire wrap on there so it'll almost hold without the solder, and then the solder just seals it up. But you really want the contact to be wire on wire, not wire on solder. So here we go. And then you want to keep it kind of narrow diameter like that so that it doesn't stick out. I hate having a big ball of solder and wire on there. It drives me crazy. Okay, I'm going to use the fine solder on this. I'll put a big blob. This is all going to be wiggling around here on us, but hey. All right. And then I'm going to cut this off at a much longer length than I need. And then we have to find some suitable insulation for it, which in this case I will probably use a piece of heat shrink tubing like this. This is kind of a narrow gauge heat shrink. And hopefully it will fit over top of this. And this heat shrink is great. I got this stuff online somewhere, really cheap, from, you know, kind of surplus. And you can't tear this stuff. It is just so strong, and it lasts really well. You can't cut it very easily. like with a hobby knife or something. It's kind of just, it's good stuff. So we'll put that on. And the problem with heat shrink is that it shrinks. So you got to kind of move it as you're shrinking it. Alright. So there we go. And to keep it from moving around, I may put another piece of the Teflon sleeving over it, like the, so right there, like that. And what I might do is put the high voltage side over here. So I'll go like that. But let me see if I have something to insulate that a little further, so it doesn't look so bad. And to cover up our sins so we don't see the splice. That looks ugly to me and I don't like it. And again, it doesn't hurt anything being there. It's just that I don't like it. I don't like the way it looks. So, that being said, we'll cover it. Okay. Heat shrink this down. It just looks a lot neater this way. There. Pretty cool. Another thing I want to do is I've been to a couple of schools lately. It's been kind of a busy year with new products coming out and so forth. And I was able to get a couple kind of interesting pictures from some friends of mine that own the school where I went. And they have a kind of a museum of some old X-ray equipment from the old days. One of you asked a question about how do the transformers compare, like the transformers that we work with here, like these audio output transformers. How do they compare to the kind of transformers that I work with at my job? And actually I saw something there at the school and I cracked up laughing because I thought of that comment immediately. And maybe I'll put that picture up for you to look at of a transformer that I used to, on a machine that I used to service back when they were still, before they were obsolete. Now, the type of transformer, these three-phase line frequency transformers, they no longer exist. Much different technology today. Transformers are, pretty much everything is high frequency now. So the transformers are much smaller. A modern X-ray machine uses, I'm talking and kind of making the solder go all over the place, but modern X-ray machines use what would be equated to a switch mode power supply type design now. It's not the same as it used to be. Okay, so there we go there. That one's connected. Now we have to connect, moving this around here. We have to connect our 470K grid leak resistors, as they call them. And these resistors, people kind of ignore these and don't really think about them, but the value of this resistor will actually set, to some extent, the input impedance to this to this next stage. So from a DC standpoint, this tube doesn't see this tube because this capacitor kind of breaks that DC offset. But as soon as you start driving a signal into there, that signal will pass right through this capacitor. And from the grid to the cathode and so forth, there is an inherent capacitance inside the tube. We call it Miller capacitance. And think of that capacitor as being in parallel with this resistor. So depending on the frequency, that Miller capacitance will act as a load, especially as you get to the higher the frequency, the more it's going to influence it. And then this fixed resistance will also act as an impedance. So basically the input impedance is going to be 470K plus the reactive component of that Miller capacitance. So by changing this resistance, you can change the input impedance of this on an AC level as this circuit sees it. So the lower you make this resistance, the more of a load that this thing will see when you start driving an actual signal into it, if that makes sense. So this does have an effect on the input. Now the other thing it can do is, the higher the resistance this is, the higher impedance you'll have, the smaller of a signal that this grid will react to. So if you don't have any resistor here, or if you have a super high, and this is about as high as you would go, 470K, if you went to like a 1 mega ohm or higher in this particular circuit, all it would do is it would make this a lot more susceptible to hum. So this kind of can control that. You'll notice in some amplifiers this can be 47 or 68K, and the reason they do that is to reduce hum. The other thing they'll put in here sometimes is called a grid stopper resistor. Quite often in the bigger amplifiers, like the ones with 6L6s and so forth, 35 watt amp, 50 watt amps, they'll put like a 1 or a 1.5K resistor in here as a grid stopper. And those actually will help to, again, with that Miller capacitance, they'll influence the frequency curve of this. But again, this amplifier was designed without it. We're not going to put that in. We're going to build the amp as it's designed and then test it. So anyway, that's just a little bit of what all this stuff does. So let's get these installed. Okay, I got the first one in here. I didn't turn the camera on, sorry. And this one goes on pin 7. Pins 6, 8, and 9 are not used on the 6P1P tubes. So you always have those 3 pins will be empty because there's no connection to them. Sometimes people will use empty, unused pins as a terminal strip on a vacuum tube amplifier, and that works great. You just have to be aware that if you go to modify it or change it to a different tube type or something, there might be something in there that you may be getting yourself in trouble, because there might be something connected to the other tube type you try to modify it to. So just keep that in mind. Now I don't have any of this soldered down yet, but we're going to do that here. Let's see if we can get this particular one to fill in, or if we're going to have to tip the amp over to get it to go. I think I have enough wires on this one to get it to bridge on this ground strip. Oh yeah, this one's going to fill in good, and it did. Okay. And then we can't finish these up until we get the input capacitors wired up. And those also connect from pin 7, and they go the first side. This side goes from pin 7 of this one over to pin 2 of this one, so it goes like this. And then the other one goes from pin 7 of this one over to pin 1, or yeah, pin 1 of this side. And there it is. So that is the other channel. I think we're all done, right? So we'll go over our work and make sure everything is connected like it should be, and kind of neaten things up a little bit. And then we'll connect our meter and see if we can get our, what did we say, about 16 volts or so on that bias resistor. Okay, we have all 4 tubes in. Let's flip this over and connect up the meter. Okay, for the moment of truth, here we go. Well, the electrons have a really hard time jumping from the end of this plug into the mains connector. So let's plug that in and let's try it again. There we go. And we had a flash of the dim bulb, and now it's dimming down nicely. Let's see, our tubes are lighting up. Looks like all 4 of them are lit up. And look at this. Let's see where this one goes. Now that we have both channels on there, you can see we had 16 volts before, and now we're only seeing about 12.5, and that dim bulb is lit up a lot brighter than it was before. So you can tell it's actually the power supply is loading down, and so is that current limiting bulb. Now we could add some current, some more current to it by paralleling some more dim bulbs in there. But before we do that, I think I'm going to go over here. I'm going to measure the other channel very gingerly here and just see where we are with this one. 11.5. So we have 11.5 and 12.5. So the 2 channels are not totally balanced, and that has to do with the tubes and some things like that. But they are both biasing up a little bit. And again, the tubes will act a little bit different under partial load than they do under full load, and that has to do with the gain of the tube. And here's why you can't match tubes just by putting an idle current through them. You actually have to put a signal through them, because the gain changes with changes in grid voltage and so forth. It can affect it a little bit because of all the surrounding components around it. So again, that doesn't mean that the channels are way out of whack from one another, but they are a little bit different. Okay, let's add a little bit of current to the signal. I added another dim bulb, and you can see now that brings that up to about 13.9, around 14 volts. And it's going to creep up as it heats up a little more. And if I look at this channel, let's see where we are, and it's about 14. So they're still not quite a volt apart from one another, but they're both well within their safe operating ranges at idle, which is good. And I would venture to guess that everything's working as it should. I don't see anything red plating. I don't think it would anyway this soon. But now let's check our. Let's just compare our anode current on both sides of the tube to see how they match up. Okay, so on the first tube we have 0.23 volts, and so 0.23 divided by 10, So again, 23 milliamps. So we have 23 milliamps on this side. There we go. So we have 29 milliamps there. So I have 23 milliamps on one side and 29 on the other. So you can see that these two tubes are not as closely matched as the other side is. They're a little bit mismatched, but that's okay. It will not hurt the amplifier one bit. Okay, let's look at a few temperatures here. So here is the main 75 ohm resistor that is feeding all the power to everything. And you can see it's only sitting at about 87 degrees Fahrenheit, 31 degrees C. And if we look at the cathode resistors, again, not that much. And if we go to Fahrenheit, so they are getting warm as we expected, but nothing too crazy. And you have to also understand, with this amp being upside down, all the heat from the vacuum tubes is radiating up onto the chassis, so it's kind of artificially heating things up more than they normally would. So again, these resistors are going to run nice and cool. So what have we learned? Well, we know that our tubes are not perfectly matched, and they weren't. I mean, they don't send you matched tubes, but that doesn't mean that when they have signal under them, that they won't be pretty close. They should be okay. And if you really want to get crazy with this sort of stuff, there's two ways to deal with it. Number one, you can try swapping the tubes around until you get the best match all the way around, if you want to take the time to experiment. And the other thing you can do would be to modify the bias circuit so that each cathode has its own cathode resistor, and then fine-tune those resistors to get the bias to be balanced out. I typically don't do that. I don't think it's worth it personally, because I don't really think that matching it at idle current exactly is going to make a huge difference, because again, when you apply a signal to it, that's where it really counts. So even if they're matched at idle current and then you start driving signal into it and they kind of drift out of match, what does it really matter at that point in time? You're kind of splitting hairs on that. But on a real high-end audiophile amplifier, you would have perfectly matched tubes, and you would probably never run them in pentode mode. You'd run them in triode mode, and you would have special bifilar wound transformers, and you would go through all this craziness, star grounding, everything, to make it have a the best performance that you could possibly get. But in these kind of little amps, you're probably not going to see that, and it's not going to make that big a difference. So I'm pleased with the way this is all working right now, and I think we're ready to move on to the next part of this build, and that is to go ahead and start building the phase inverter section. So that'll be the next video, and until then, I wish you all peace, joy, happiness, and good health in your lives. Let's get this video up there. We'll get it edited, and we'll be back soon. Take care. Bye-bye. Look at that thing go. Where will she pass balance?